Firstly, I wish to extend my deep sense of gratitude to State House for reaching out to the Namibia University of Science and Technology to host this prestigious academic gathering, as initiated by His Excellency the President, under the heading Professor Juma Memorial Lecture, Public Policy Options for Science and Technology in Africa. In addition to NAS being Namibia's only technological university, with a core mission that embraces science and technology, research and development, entrepreneurship and innovation, it is also the natural home for public discourse on any relevant scientific or other development topics. In the same vein, I'm deeply honored to provide a high-level reflection on Professor Calestous Juma's unfinished paper titled Science and Technology Advice to the Presidency. I'm humbled by this opportunity to comment on the scholarly work of one of Africa's preeminent intellectuals. I shall not critique the paper. I will rather highlight the critical issues raised and the recommendations postulated. The paper consists of 5 sections or chapters as follows. The first section presents the key features of Africa's technological vision as expressed in the various presidential summits convened by the African Union or AU. Section 2 examines the key global trends in presidential science and technology advice. Section 3 or Chapter 3 provides an overview of the institutional arrangements and models used to provide presidential science and technology advice. Chapter 4 uses the case of Namibia to illustrate how structures of government, often arising from national constitutions, can hinder or facilitate the effective provision of presidential advice. And the final chapter, 5, outlines various options that could be pursued to strengthen the institution of presidential science and technology advice. But first, as we embark on this analysis, I shall provide a synopsis or reflection which speaks to the background against which the paper is framed. To be clear, the paper analyzes Africa's development scenarios and challenges in science and technology, research and development, and innovation, and proposes various solutions based on best practices. But it does not impose a particular solution for a particular president, government, or government system. These 5 indicators, science, technology, research, development, and innovation, are measures or indications of or potential for socio-economic development. For instance, the index rank of science and technology capacity indicates the status of a country as scientifically advanced, scientifically proficient, scientifically developing, and scientifically lagging. Thus, expenditure on these 5 development factors is a key indicator of government and private sector efforts to obtain a competitive advantage in science and technology. It is a proven fact that science has helped stimulate economic growth in regions investing in innovative solutions around the world. However, in respect of all the 5 factors, Africa lags behind, thus making the case for stronger scientific and technological advice, foundations, renewal, and revival more urgent. In other words, a number of African countries are poised to reap the economic benefits of increased investment in science and technology, expressed as a percentage of the national gross domestic product or percent of GDP. For example, while the global R&D expenditure for the world stands at 2.27% of GDP, for Namibia it reflects a meager investment of 0.34%, much lower than the agreed 1% of GDP. In contrast, Namibia's military spending stands at 1.8% of GDP, with little investment in R&D on its part. It's clear that we're not building a knowledge economy. Some would say we're building a military economy. But there is academic freedom, I've had it been said many times. On this turf, I am protected, so I can say whatever. I've seen that literally sometimes in the barracks when I go home. The paper highlights that while the above indicators are foundations of development. These are strongly linked to tertiary education enrollment. Tertiary foundation must fulfill the role as drivers of growth and technological capacity in research, development, and innovation. But once again, Africa's tertiary enrollment rates among the lowest in the world. The average for Africa is 7.1% compared to 25% elsewhere in the world. This evidence shows that African countries still lag behind in science and technology capability. As African countries advance in science and technology capability, their changes of orienting economies towards sustained and sustainable growth are greatly enhanced. It is for these reasons that the paper on science and technology advice to African presidents will play a critical role in shaping policy frameworks. In the introduction, the paper briefly sketches the history of presence of Western technology through innovation and colonization, when technologies were employed to subjugate African populations and exploit them, resulting in racial and power imbalances. And it further sketches contestations between indigenous and Western technologies. Following colonization, economic integration and transformation of Africa became possible, leading to the replacement of the OAU as we thought, which was which was driven by political and decolonization agenda, with the AU, which is driven by a development agenda. To the extent to which the mentorship is reflected in the organization of government, so they can serve as facilitators of technological innovation, is one of Africa's emerging policy challenges. They require Africa's political commitment to moving the economies from being resource-driven to being innovation-led. Let's not delve into the details of the 5 chapters one by one. The introduction deals with the key features of Africa's technological vision, as expressed in the various presidential summits covered by the AU. This mentorship alludes to earlier this mentorship alluded to earlier led to the adoption of the AU's 10-year science, technology, and innovation strategy for Africa, or STISA 2024. This is a policy orientation meant to accelerate Africa's 50-year Agenda 2063, aiming for inclusive growth and sustainable development. The strategy accounts for Africa's contemporary levels of development, their persistence, and is about harnessing science, technology, and innovation to help solve 6 key challenges: building infrastructure, eliminating hunger, improving human development, protecting the environment, enhancing social cohesion, and spreading prosperity. All in all, the importance of harvesting science and leveraging existing technologies and discovery is necessary to drive development by creating new enterprises and expanding development growth options. This approach also includes fostering innovation through interactions between government, academia, business, and civil society associations, their contributions. Therefore, STISA 2024 has identified 4 strategic actions that reflect Africa's state of development while accommodating different states. And these are investing in infrastructure, both physical projects and research facilities, building technological and technical capabilities, incubating and upscaling enterprises, building the innovation state. This requires creativity and flexibility from African policymakers and from them to act as agents and champions of the innovation state, thereby providing coordinated policies that fit specific purposes. In short, the African countries need to create governance structures and policy environments that nurture innovation and enhance continuous policy adjustment. This is best achieved with the support of offices in science, technology, and innovation advice for heads of state and government. The paper points out that no African country has such a statutory office, whose function would be to advise on how to incrementally adjust governance structures to support innovation. And as such, an approach will leverage the country's regular investments in infrastructure, education, and entrepreneurship to support innovation. The paper also highlights that making innovation a routine aspect of existing activities involves less additional financial investment than other routes. Chapter 2 provides a synthesis of lessons learned worldwide, speaking of codification of practices in various countries, mostly in industrialized world. Thus, the principles of science and technology advice stress the importance of quality of advice and selection of the appropriate principles to fit national realities, underlining the use of democratic principles such as openness, effectiveness, and policy advice, and continuous institutional self-review and advisory mechanisms. The paper puts forward the notion that Africa's take to science and technology and innovation advice has been based on political appointments of presidential advisors, designating existing ministers to serve as advisors, and creating advisory councils. These approaches reflect the nature of national constitution structure, limited financial and human resources, and lack of legal capacity to sustain science and technology advice. The problem is accentuated by the nascent nature of national scientific academies, or lack thereof. On the other hand, the quality of science and technology advice depends on maintaining quality expert advice, which depends on a variety of conditions that include early and appropriate identification of issues, recognition and appropriate treatment of scientific uncertainty and risk, and diversity of opinion and cross-disciplinary approaches. However, the main problem is Africa's countries' institutional arrangements that foster advice while hoping to maintain independence. This is influenced by domestic conditions such as funding and robustness of scientific, engineering, and technological community. Therefore, the advice is that early and appropriate identification is a key aspect of the quality of presidential advice on science and technology. There is a need for building science academies to interact with the public, with politicians, and the wider scientific community. In summary, the quality of science and technology advice depends on various preconditions, such as qualified and quality advisors, diversity of views and cross-disciplinary approaches to scientific questions, accuracy of scientific advice based on scientific evidence, analysis, and conclusions, financial, intellectual, and political independence and disinterestedness in outcomes, public trust in information and public in policy based on appropriate and sound active mechanisms, inclusiveness and openness to all institutions and sectors of society, and finally, review and feedback. Chapter 3 explores 4 models derived from an analysis of existing review and feedback mechanisms, best practice comparison. 1, the agency outreach model, which is more like the triple helix that we spoke about a bit earlier, engaging all stakeholders in society. He says that this may require resources that developing countries do not have or cannot afford, but it's more like resources that we have but we don't invest in the model. It expires unconstrained. The second model is independent advisory model for private setting, which is more suitable for developing economies and involves the science agency as a leader that seeks advice or input from an objective group. The third model is a convened science advisory board model for priority setting. And this is an advisory committee that can have members with several year terms and can be convened to advise on scientific and engineering advice. So they provide external advice. The fourth model is a network model of science, which draws advice from sectoral advisory mechanisms to inform national decisions. For example, a chief scientist in the president's office coordinates input on specific issues from across the different departments. This requires extensive financial and institutional resources. Given the various models, the paper continues to probe the question of institutions of presidential advice. It recognizes that advising presidents happens at all government levels, as advice can be sought in various ways. The primary difference between advice mechanisms exists as follows. At which level is scientific input received? How formal or flexible is the advisory process? What is the relative use of science advice in different branches of government, executive and legislative? And to what degree are advisors involved in the decision-making process? The establishment of institutions to advise presidents should be structured to consider organizational, financial, and political characteristics of the country. There is scope also for scientific and engineering academies and science and technology advisors, which should be established and maintained as one way of realizing professional advice. Academies can grow from the scientific and engineering community independently, but they can also grow through concerted efforts by the government. In other cases, funding and resources shape both the conscious innovation and natural evolution of academies. The paper recognizes institutional obstacles that can hinder establishment, evolution, and success of science and technology advice, and some of these are lack of political will, often attributed to the president. It's not from me. Financial capability and sustainability, and constitutional, legal, and institutional parameters. I still hope I get invited to State House. The fourth chapter deals with presidential advice in Africa, the case for Namibia. In this chapter, the paper studies Namibia's constitutional, legislative, governance, and executive provisions in order to frame a case study for Africa. Unfortunately, the work wasn't completed, and there are no firm recommendations on science and technology advice for Namibia as involved. But it is evident that a model or a hybrid of models proposed in the paper are workable solutions for Namibia and Africa. The torch has been passed on to the current and future generations. The job is unfinished. And chapter 5 deals with advice on strengthening presidential science and technology advice. It is essentially a capstone project crystallizing presidential advice in science and technology. It proposes 5 solutions. 1. Adopt a high-level strategic vision for innovation and development. 2. Reform the various branches of government. 3. Build capacity to manage advisory processes. And 4. Improve funding and legal capacity for advisory activities. These could be the building blocks for establishing a dedicated office of chief scientist in the President's office. In order to enhance public accountability, legal arrangements or instruments should be put in place. But all in all, it should be understood that advisory offices do not have implementation functions in the same way as do presidential academic advisors. In conclusion, the paper has outlined the increasing importance of science, technology, and innovation as major sources of economic transformation, and has presented key concepts, procedures, and institutional arrangements needed to strengthen scientific advice. An indicative roadmap includes adopting a high-level strategic vision for innovation and development, reforming the various branches of government to reflect a coordinated approach to science and technology advice, diversify advisory mechanisms and procedures to reduce uncertainty, build capacity to manage advisory processes, and improving the funding and legal capacity for science and technology advice. There is no viable alternative to adopting an evidence-based approach to decision-making and codifying the activities of law and institutions. Once again, I thank you for the occasion to present this synopsis on this commemorative paper.